We've seen that eigenvalue equations have a very special form, and I'll rewrite that here, that if f is an eigenfunction of an operator a, that the operation of a on f will simply give a number a times that function. So how does this come up in practice? I want to give you a quick example just to illustrate this. Now, you may recall that the momentum operator has a rather peculiar form. It is equal to IH bar ddx, minus IH bar ddx. So one might wonder, what are the eigenfunctions of the momentum operator? All right, can we find that out by applying this eigenvalue equation to it? Okay, so let's suppose that we have some function f that is an eigenfunction of p. So if I operate p on f, that's the same as taking minus IH bar times the derivative of f. And now the eigenvalue equation says that that should equal some constant, and I'll call that constant alpha, times our function back again. Okay, so if we take this equation and we divide both sides by minus IH bar, I'll end up with a first order differential equation that looks something like this. Now when we divide by minus I, that's the same as multiplying by I, so I'll put the I up top, then divided by h bar, and we've lost the minus sign, and times f of x. Okay, now as we have done in other circumstances in the fall course, we could divide both sides by f and multiply both sides by dx, and we could end up with an equation that looks something like this. df over f is equal to I alpha over h bar times dx. And then integrate both sides. Okay, when we integrate both sides, we'll get log of f is equal to I a over h bar times x. Okay, now I need to worry about an integration constant in this, so I'll just say that let's say there's an integration constant that gives us a ratio here of f to f0. It won't matter too much, but I'll do that just for completeness. Okay, well, when I solve this equation for f, I'll end up with, when I raise both sides to the e to both sides of the power, we'll have f of x is equal to e to the I alpha x over h bar. And in fact, since I've got this over f0, I'll make it like that. So our final result, maybe we'll put this in a different color, would be f of x is equal to some value e to the I alpha x over h bar. So this is our eigenfunction for the momentum operator. Okay, and our eigenvalue here, alpha, shows up in the numerator of this function. So that means there's no restriction on alpha, so that means any value will work as an eigenvalue as long as the function has this particular functional form. Now we can demonstrate that this in fact is an eigenfunction by going ahead and applying the momentum operator to f of x. So minus IH bar d dx times operating on f0 times e to the I alpha x over h bar. And the differential won't have any effect on f0, so it will come out front. So we'll have minus I h bar f0, and then the derivative of what's inside here is going to mean to bring down the I alpha over h bar. And it will leave the exponential. Okay, that would be the effect of taking that derivative. Okay, so if I bring this stuff out and multiply it by IH bar, well, minus I times I gives us 1. H bar over H bar cancels, and I'll end up with alpha f0 e to the I alpha x over H bar, but this is just my original function. So in fact, what I've demonstrated is that that function does satisfy this particular relationship where f is an eigenfunction of the momentum operator with the eigenvalue alpha. And so that's how eigenvalue equations work, and that's how one might in principle find the eigenfunctions and even possibly eigenvalues for a given operator.